record first. It will cover until this chapter, until this module, the module 4. So remember, your test will be next week, right? On 18th of November. Okay, 18th November. So I hope you can study and do a very thorough practice on the instruction set that we have covered, and also those in the instruction set. Okay, so in your test later on, please do not expect that whatever we have here will come out. Okay, sometimes in instruction sets, whatever in instruction sets, they can ask you. Okay, but because you have that instruction set, you can refer to instruction set during test and final exam. So anything from the instruction set can come out, right? As long as you understand, as long as you understand the description, how to do that. Okay, it will be easier for you. Okay, so let's start. Okay. Can someone please respond to me if you can see this slide or not, or maybe you can hear my voice.
Yes, doctor. Okay. Can see as well.
Right. Okay, good. So I will not cover these first slides. I hope you guys can read it. Okay. So particularly what we want to know today is we are learning assembly language, right? And then after the half of the semester, we're going to high level language. Okay, you have learned high level language before, but it wasn't used for hardware, right? But for this class, for this course, you're going to use high level language to program your hardware, right? So it will be a little bit different, right? So I will not cover this. Please go through and read it. Right? We've seen this before. Okay, and okay, you have seen this example also. You have seen this kind of this program. In fact, you're way advanced than this. Okay. Okay. Remember to tap to tap before writing your instruction set, your mnemonic, and over here you reserve it for label. Okay. Right. So in assembler, in your AVR assembler, you will see that when you press compile or when you press debug or something, you will see this this code, right? This some kind of this number over here on the left. That is your what do you call it, the flash address, right? The address shown by the assembler. Okay, the assembler show the address of program memory, the code memory, right? The flash. Okay, what it stores is it stores this instruction set, right? This this machine code. The machine code. This one is the one that when we discuss about CPU decoding, right? CPU decode the instruction. This is the instruction. This is the instruction in machine code. So you need to decode it, right? So you need to decode the instruction so that only then it understand that it is actually load immediate R16.9. Okay. So in instruction set, right? In assembly language. Okay. So yeah, this is the thing that we need to focus. Okay, I will focus only on beginning from this slide on. Right, we're gonna see. Okay, the AVR assembly directives. So the most commonly used directives are this one: byte, C seg, code segment. Okay, C means code, segment. Okay, you will see another one, D seg, means it's a data segment. Okay, data segment over here, it means data. Okay, so remember, code means the program, right? Program memory, and data is for data memory. So we are going to see that later. What is the difference between these two? Okay, but please remember, when you see C and you see D seg and C seg, they are different in terms of memory. Okay, DB as a defined byte constant. Define a constant, but it is in byte size. Okay, and DW means define a word. Okay, define a constant, but in a word format. Means word means 2 bytes, right? And DEF means define. You're defining something, a symbol, a register, or something. Okay, and okay, this one. EQ. EQU means equate. Set a symbol equal to an expression. We're going to use that also. Include is very common. Okay, include means we include the other files. Okay, we usually use this include to include other files into our current directory, or into our current file. And then we have org, and then we have set. Org, okay, we have seen this last week, that we set the program to original, right? The program means as in flash program to start, right? So if I put .org 100, it means that we need the program to the CPU or the program to start storing the code beginning from program 100. Okay, we'll see that later on. Okay, and set is another symbol to define an expression. Okay, so all these directives will be used, and I will try to show as many as possible for the program that we're going to see today. Okay, so for the first one, this one is include. Okay, just like I mentioned just now, include another file. This one is to include another file. For example, this is the file of IO definitions, so ASM, and this file that we write, we just call another file. You use include IO defs and the file name is okay, and so on, right? It's simple as that. So for AdMega, okay, we usually include this file m32 def.inc. Okay, that means file, the library. Okay, the library for it to understand. And .org is a program. Okay, program origin means that we, like I told you, okay, where we set the flash. Okay, meaning that we are telling the compiler to store the program, the code that we write, starting from what address. Okay, and flash memory is affected. Okay, not the data memory, only the flash memory, right? All right, this is the example, like this one. Okay, the org. Okay, just ignore the other directive first. Just look at the org first, right? Okay, like this one. Okay, this one, and this one, right? After that, this is dot byte, right? Reserve. When we do dot byte, means it reserve a bytes to a variable. We reserve a byte to a variable. Okay, so if for example, look at this. Okay, so before that, all right. Next thing, this one is first thing you need to know is it reserves a byte. Okay, it reserves byte according to what we define. If we want it to reserve 2 bytes, then it's a 2 byte, then we write 2 bytes, right? But if it is 1 byte, then it's just 1 byte. And when we define it in byte, it means that it reserves the memory. Okay, reserve memory in SRAM. Remember, SRAM starts from, is Neoma here?
Yes, bro. Yes, doctor.
Okay. What is the starting address of SRAM?
60.
60, right? So 60, meaning that when we reserve a memory resource in the SRAM, it starts from 60. Okay, so if we say, one more question, Nick Omar. So how many bytes does SRAM hold for each memory location?
2
What is the
kilobytes.
size? Sorry?
2 kilobytes.
Come again? 2 kilobytes?
Yes, doctor.
Okay,
No, eight.
so you are referring to 2 kilobytes, but I'm saying what I mean is that for one memory location, what is the size? What is the data size?
8 bits?
Yeah,
8.
8 bit.
8
Okay,
bits.
8 bits, right? Okay, right, good. So 8 bits, right? So 8 bits. So meaning that when we reserve a byte, it means that it reserve one memory location. Understand? So if I say I reserve 2 bytes, meaning that it reserves 2 memory location. Simple, right? So if I say 1 byte, so it's only starting from 60. So if it's 2 bytes, means 60 and 61. Understand? So it must start from SRAM starting from 60. Okay, so meaning you reserve the bytes, even though you're not allocating anything yet, but you are reserving. You reserve that location, right? Okay, for example, like this one. Okay, var1 is reserving 1 byte. So meaning that straight away it goes to SRAM. Okay, byte. Okay, because why? Because I will tell you later. Okay, if you just out of curiosity, if you ask, this side here means that data, right? Data memory. Like I told you just now, data memory and code memory. Okay, data memory is SRAM, code memory is flash, right? So if whenever you see .d side over here, it means that we start using the SRAM. Okay, we allocate whatever beneath whatever under the D seg, meaning that everything is written in SRAM, and whatever is defined or declared after .c seg, all this goes to flash. This one goes to SRAM. Okay, because it's data segment. This one is code segment. So it's for flash, right? So something like that, and okay, like that. Okay, so here you'll find other than this one, you will find you will find .equ dot after eq dot set. Another one is equals set, and one more is define. Okay, so you will see that they are all almost the same. I mean, like you can use them like arbitrary, like randomly, right? So we'll find what's the difference between them, right? EQU means equal, means that you are setting a symbol equal to an expression, just like this one. Just like you define a constant, right? Define a constant with 23, just like your C program. Okay, and another important thing to know is that it cannot be changed or redefined. Okay, once you define it, it's like a global parameter, right? Global parameter where you cannot change it. Okay. Sorry, global parameter. Can you change the global parameter? I don't think so. Okay, but private, yes. Okay. local parameter. So for this one, okay, for this example, okay, IO offset. So when you can call IO offset wherever you want in your program. Okay, you can program and then you call wherever IO offset, and then what it will return? It will return 23. The value, it will return value. It will not return the number, the name or the variable, but it returns the number. Okay. So when you write it, when port A, so what you will understand is that port A is IO offset plus 2. So meaning that it is hexadecimal 23 plus 2 means hexadecimal 25. Okay, just like I told you, set is another example where you can equal to an expression, but it can be changed. Later in the program, okay, if you use, okay, just like previous, same variable from the previous slide, okay, but now we use set, okay, so it's the same, okay. The only difference is that it can be changed later, meaning that under when you have already declared this, and then inside the C set you again declare or write a dot C set, dot set as IO offset with another value. It will take the latest value. Okay, so if you override, you override the previous value. Can do that for set. Now, yeah, I told you about code C set, right? Code segment. Okay, so meaning that we are telling the program, okay, to define the start of a code segment. Okay, meaning that we are telling the program beginning from this onward. We are saying that we're telling the compiler, hey, the compiler, please, starting from this onward, this line onward, please store everything in flash memory, right? So starting from C side over here, it will go to program memory. Okay, it will store to program memory. And for the .dsec, meaning that whenever the compiler says .dsec, meaning that it knows that it needs to store whatever is defined under .dsec in RAM, okay, SRAM, in SRAM. So if you recall, here var type .byte 4, meaning it stores 4 bytes. I mean, it reserves 4 bytes, right? In SRAM, starting from memory 60 until memory 60, 60, 60, 61, 62, 63. Okay.
Three.
Okay, you're late. You're given a chance already. Pass. Okay, so 63, right? So if, okay, for example, I have another question. If let's say var type byte 4, and then I declare another variables, right? Like for example, a hello, right? A hello variables, right? And then I declare byte 3. So how does it? Where will it start? It will occupy 3 bytes. Okay, what memory will it start? It will start at memory 64.
Yes.
64, right? Because var type already take. Sorry, what? Okay, so because var type already reserve 4 bytes, meaning 4 memory location, 1, 2, 3. Or how many of them? Okay, anyway. So there are 4, right? So 60, 61, 62, 63. So starting from, okay, let's just consider there are 4 here. Okay, so 63. And then for hello, it will append, I mean, it will continue from the previous, from the last memory, the end address of the last variable. So we start from 64 and it will take 64, 65, 66. Okay. So this one for hello, this Okay, this one is for Varta. Hello. Okay. Okay, so data segment. So data segment, okay, we just saw that. Okay, we just saw that just now. So I just keep ESEG. ESEG is for EEPROM. Okay, EEPROM means that we are defining, we are telling the compiler, please use the EEPROM memory to store whatever we want, right? So we are telling that one is for EEPROM. Okay, .d byte. Okay, d define constant in byte, right? So here is define constant in byte. Okay, where is the in program memory or EEPROM? We are just define. Okay, we are not reserving. We do not reserve the memory, the location, but we just define. There's a constant. We want to use the memory, but we do not really use it. Okay, we do not really use it. Okay, for example, for when we declare C-sec over here, it must be, okay, remember it must be only in program memory or in EEPROM. Okay, so .db 0, 25, 255, okay, we can declare any value here. Okay, you can declare, meaning that if you have a program, later on in your project, you have a thing that you want to fix it, you can just use .db, right? .db just to show there's for example, there's an array, right? An array. So you can just define it in here, .db. So it's like meaning that you're telling the program, okay, please store this because I want to use this for my for CPU processing or something. Okay, so we you can use .db. Okay. .dw is the same, but it's just the difference is just it's in word, right? So you need to know the range. Okay, the range the word can allocate, right? So meaning that in this case it is it is a signed number. Okay, it can be signed and unsigned number. Okay, same like this one. Okay, forward for bytes. .def. Okay, okay, I just told you. Okay, so we have seen EQU means equate dot set, and now we've seen def. Okay, so which one cannot be changed or cannot be redefined?
EQ.
Okay, the first one, right? EQU. So for set and def,
EQ.
okay, for set and def, okay, set can be, okay, you can change, right? You can redefine, but for def, you need to only use it for registers. Okay, only for registers. So when you see .def temp R16, meaning that whenever you call temp, it means it returns a register. Okay, a GPR, right? Register value. So for example, like this one, okay, CSEC, LDR, temp F0. So F0 will be loaded into R16, and 3F will be loaded into R0. Okay, like that. So remember, def is only for register.
Can it be changed, Doctor?
Sorry?
Can it be changed, the value?
Yes, it can be redefined.
Yes.
Okay, meaning that after that you can redefine.
Doctor,
that.
can you repeat this?
Okay, when we see def here, it means that we can represent a register with a number, with a name, with a variable. Okay, you can, for example, you can represent R24. Okay, R24, register R24. You can for example .def. Okay, R24. Let me write it again. Okay, for example, def, what do you want to write? For example, kira, okay, def kira. Kira means count, right, in Malay. Kira R24, meaning I'm saying that whenever I use LDI, load immediate something. For example, I want to load number 16 into kira. So what it does is that this number decimal 16 will be stored in R24. Actually, it's R24. And remember, R20 def or DEF here can only be used to represent a register, a GPR, okay, a register. You guys understand this? Okay, so it's different with EQ and set. EQ and set can represent a variable. I mean, can represent a value, a constant, right? Whatever value. For example, like this one, kira. If you want LDI kira, let's say you put EQU dot EQU what? Susahnya nak kira. Alif, for example, alif. Okay, EQU alif equals to 16. So you can might as well just call learn immediate kira alif. Okay, you can use that. So you don't see, you don't get to see the value here, but it's actually calling the value, okay, because these are variables. Okay. Any other question? Okay, exit. Okay, finish. Any question?
No.
Yes, one question. For data segment, can you repeat that part when it stores starting from 60 on SRAM?
Yeah, okay. Whenever, okay, for data segment, right? When we define .dseg, whenever the compiler starts saying .dseg over here, it means that we are telling the compiler, okay, we're telling the compiler to write or to store any value or whatever we define beginning from then onward until it sees .cseg. Okay, whatever before .cseg, like this one, it will be stored, okay, starting from memory 60, because our SRAM is because our SRAM starts from memory 60. I think somebody need to
Karim, mute your voice.
Okay, all right, thank you. So .dseg meaning that we are telling the compiler to start storing, okay, whatever variable that you define afterwards, after this .dseg, starting from memory 60. What is 60? Because 60 is the start address of SRAM, right? Okay. If you remember, if you recall, our data memory consists of the first 32 addresses GPR, and then the second, the next 64 memory locations for SFR, and the last one is for SRAM. I mean RAM, right? So this one starts from memory 60, correct? So when we start from memory 60, this is what data segment is will allocate our variable here, starting from memory 60. Understand?
Yeah, understood. So, for example, if it says byte 5, store this in byte 5. So it counts from
byte 5, like this. Yes. Yes, starting from 60 and end at 64.
Oh, so it ends at 64, not
Okay.
65.
Yes, of course, not 65 because 60 is still a memory location. That is the start address of memory location. So, okay, understand?
If
So,
if I define another byte, reserve another byte, it will start again at 65. Then.
yes.
Okay.
So this is 5. So you can visualize it, right? This is from 60. Okay, will occupy all 4 bytes. All five bytes, meaning 5 memory locations. So it will end up at 64 for 5 bytes, right? 60, 61, 62, 63, 64. How many bytes are there? 5. So if you have another variables that you declare after that, you will definitely start with a new memory location at 65. Understand?
Yes.
For example, you have table byte 2. So it will occupy, okay, for this part over here until 64, this one is allocated for var1. For table, 2 bytes, right? So 65 and 66. Starting from this until this one is stable. Okay, it is not simply as 60 plus 5. Okay, we use 65. If you do that, okay, meaning that if you imagine it in that way, you are telling the compiler it is as if you are not utilizing 60 memory address 60, meaning that you just ignore memory 60. You just start storing from 61. Okay, it's not like our addition, our mathematical operation, just 60 plus 5 is 65. Because in computer we use 60. Is this sorry?
Doctor, I can't hear you clearly.
Huh? Sorry? Can you hear me?
I can't hear you clearly.
You cannot hear me?
I I didn't hear the last sentence.
What was my last sentence? I forgot. Okay, anyway, so okay, in a nutshell, okay, in conclusion, it's not like calculating, or it's not like we're doing the addition operation like mathematics. Like we mathematics 60 plus 5. Okay, it's like I understand when you do 60 plus 5, I mean you imagine that we use 5 bytes means 60 plus 5, then it will utilize up until 65. Is it correct? So was it what you think?
No, it's wrong.
No. Okay, so if it is not, then that's good. But if somebody thinks about like that, okay, it's definitely wrong. Okay, so because you need to know that when it starts from 60 and utilizes 5 bytes, meaning that 60 is counted. Okay, like that. Okay, so you have to consider the start address and end address of whatever you you put. Okay, any other question?
Okay.
I hope you guys will see this more clearly in when I show this program. Okay, I'm sharing another. Atmos Studio. Can you guys see this now?
Yes, you can see it.
Okay, this is just an example. It's not really a test one exercise. Okay, I was thinking of to give you an test one exercise, but I think I need to show this one first to you. This one is for additives, right? Directive, our current topic. So this one, this one I'll try to simplify as much as possible, but maybe there will be some, I need to do some correction. I haven't really done it right. Okay, let's see this. Okay, so this is the C sec. Okay, when you write the program, the C sec over here. Okay, let me. Never mind. That's just. Okay, let's see set over here. Okay, C set is a code segment. Okay, meaning that we are telling the compiler, like I told you, we are telling the compiler starting to use this program memory. Okay, to store all this starting from below until I see .tsec. Okay, I stop until here. All this will be stored in code segment in a flash memory, right? Right. After here, after that, I write .dsec like this, meaning that I'm telling the compiler, hey, number one and number two, please store this whatever variable here in data memory, right? Meaning starting from, please allocate memory for these variables, right? In RAM and SRAM. Right. So starting from here onwards, the ORG100, you can later you can check that, right, in flash memory. And .eq over here is addition equals to 3, meaning that we are telling we give a memory a variable with a name addition is equals to 3 equal loop equals 64 dot set its result is 50 define kira R24. Okay, remember define is only for register. Okay, dot def is only for register. Okay, this one is just a regular thing. I just want to store value that I have in R20 until R24 5 to show there's something in my memory. So okay, so I will see something in my memory over here because later on we're going to do some processing. Okay. All right. So so load immediate R26 result. So what we do is going to load memory value 50 to R26, sorry. And then loop plus 5 means loop is 64 plus 5. Okay, you can do that, right? You can plus 5, you can times 2, you can times, okay, you just do whatever processing you want. Okay, and just, okay, like that is for multiplication or divide. Okay, divide by 5, you can do that as well, right? And then store inside 16. Okay, and number 2 plus 2. Okay, this is interesting. When you see this number 2 plus 2, what do you expect? Can somebody please answer my question? What do you think is this going to happen?
Store value of 5 in the register R26.
Can you tell your name and answer
البراء
and try to explain?
البراء in the register
Elbara, okay, Elbara, yes.
for the register R26 to restore the value number 2 which equal to 3 plus 2 means in register R26 the value will be 5.
Too fast. Come again. Too fast. Again.
Yeah. Again, in the register R26 it will load the value of number 2 plus 2. Number 2 is
right.
equal to 3. So 3 plus 2 will be equal to 5. Meaning that in the register R26 the value will be loaded 5.
Oh, good try, but unfortunately it's wrong. Okay, so okay, next someone else who wants to who understand my lecture just now, who can explain to me, who can explain to us about this. I think I've explained about this 2 times already in the slide. Somebody? Albara, please mention a name. Call your friend's name, who you know to explain.
My friend name Azhari.
Sorry? Azhari.
Yes.
Okay. Please, whatever, call, please respond. Azhari, I think Azhari.
Yes, doctor.
Okay, please. I highlighted that LDS are 26, that one. Please explain to me what's going to happen there.
Okay. The number 2 represent by 3.
Mm-hmm.
Okay, so number 2 plus 2 and load in R26.
So what before that, number 2, what does it represent? What
Byte
value?
value byte 3.
So
It's loaded in register 26 in
you
SRAM.
mean it will be 3 plus 2, meaning equal to 5, and then will be loaded to R26.
Yes.
Unfortunately, wrong also. Anyone else?
Doctor, that's a both increment, right?
No. When you say increment, okay, you have to understand. When increment is only for XYZ register. Remember? In instruction set, if you remember last slide, okay. Yeah, I mean, I understand when you say increment. Okay, also because you see it's plus 2 over here. Yeah, it's incremented by 2. But what I'm referring to when you say increment, it means that I understand it in increment by 1 like that. Okay, but this one is just okay, just what do you call it? Increment or addition of 2 to the current storage. Okay. Anyone want to try? I will explain after this.
I don't know, but I'll try.
Who is this?
It's Mu'min Ali.
Okay, Mama Ali.
So in R26, it will load number 2, and after it loads number 2, number 2 itself will be incremented by 2.
Number 2 is
it will be byte 4, I guess. Byte 5.
What is the current number of number 2? What is the current value that it holds in number 2?
In number 2, it holds 65. 65 of memory, so it will be incremented by 2. 67, I guess, after the increment.
65. Okay. It's almost there. Okay. Since it's 251 already, let me explain it. So what is going to happen is that this number 2, okay, is referring to memory location 64. Okay, starting for 64. Why? Because number 1 already occupied or already reserved 4 bytes, right? So 4 bytes starting from 60. Remember 60 SRAM. So 60, 61, 62, 63. So that one goes for number 1, right? So number 2, there are 3 bytes. So what you will do is this one, number 2, will take the first memory location of number 2. The first memory location of number 2 is
64.
address 64, right? So address 64, okay, plus 2 means address 66, right? So address 66, okay, please look at here, LDS. LDS here means load from storage. It means that we are taking the value pointed by number 2 plus 2 means address 66, right? Address 66. So what is the value in address 66? Then we take it and then we store it in R26. We do not, okay, please do not confuse, okay, please do not be confused between LDS and LDI. Load immediate, LDI is for constant, for any value. For any value means that over here, loop 5, loop plus 5, loop is 64 plus 5, 69. Straight away, you take R16. But LDS means we take from storage, we take the value, not straight away number 2 plus 2 over here, and then we translate it into number and then we immediately store it into R26. No. Remember, when there's a S here, means we take the value from what it points here. This one is pointing to the memory location. So we take the value in the memory location, right? 66. What is the memory address? Is 66. What is the value inside it? The data inside it, that's the value that we want. And then we put it in R26, right? That's a difference between LDS and LDI. Okay. Load immediate is a constant. We take the constant value. Straight away, we assign it into any registers and the destination register. But from LDS, remember, we take from the memory. We must take the value from the point.
So the LDS, the source, so the LDS is in hand. Like in LDI, the source operand is a constant. So it's a number, it's a data, right?
Yes, that's why load immediate. When you see I means immediate, a constant. It's a constant. So the operand, so the source is simply a number. Okay, you simply assign a number into a register. But LDS, you are taking the value pointed by this address. Value means data pointed by this address in RAM, and bring that data into R26. Understand? There's a difference between storage, LDS, and LDI. Understand?
Doctor.
Yep.
Doctor, I have a question.
What?
Number 2, it is referred to dot by 3, right?
Referring to?
Dot by 3.
Yes. Dot by 3.
So, starting from memory location 64 until 64, 65,
65, 66, right? But, yes.
Then, do we need
Yes.
do we need to take 66 plus 2 or 64 plus 2?
64 plus 2. We take from the first memory address. 64 plus 2.
Okay.
Understand?
Okay, thank you, Doctor.
Okay.
I have a question, Doctor. Number 2 should be constant or should be in hexadecimal?
Number 2 is a constant. What do you mean? Number 2, this is just variable. You can just give any name. This one is name, okay? Whatever variable name.
No,
okay?
no. I mean the constant too.
Oh, this one over here.
Yeah, because
this one just constant too. You can just put decimal. You can just put hexadecimal. Whatever. You can even put binary. But what the compiler will do, it will translate it into hexadecimal.
Okay.
Okay.
Thank you. Okay.
Right. So right. So I don't know if I have time. I can explain it, but continue. Okay. So I will continue. Very quick one. Okay, this one just storing the value into R24, for example. Okay, so what I'm going to see is that we're going to see in memory, we are storing the value of R25 and with this value. Okay, we're copying it from registers, right? So you see in RAM over here. Now we are starting this one, R26. So results. Load immediate R26 from results. So result 50 goes to R26. So we're gonna see simple as that. So R26 is loaded with 50 now. And then R16, loop 5, loop plus 5. Loop plus 5 is 64 plus 60 plus 5 is 69, right? So R16 is gonna be updated with the value of 69, right? Okay. 69, right? Okay, this one is interesting, right? So what do we expect? So we know that just now we are saying that number 2 plus 2. So we know that number 2 start from address 64 plus 2 66. So what is the memory value? So data in memory 66. This one 61 and 60. Sorry, this one is 60, 61. Okay, the memory 60, 61, 62, 63, 64, 65, 66, right? So we start from 64. 64, but plus 2. So we have to go to 6F, right? Over here, this is 66. So we are expecting that number 2 plus 2 is 66, memory 66 is 6F. It will be loaded into R26. Okay, let's see. R26 is currently 50, so what is going to happen? Okay, so it copies, right? So 6F, right? So we are right, we are correct. 50F is copied and then it goes to R26. All right, so for this one, STD store with displacement, right? Store with displacement is Y plus addition. Okay, so Y plus addition, you remember, Y plus addition meaning that we go to Y, sorry, R25, whatever value in R25 will be stored in Y plus addition. What is current value of Y? Y is showing 75. Last addition is 3, so it will be 78, right? So it will store in memory 78. Okay, it will be stored in memory 78, but will Y be updated or not after that? Will Y be updated? No, okay, because it's displacement, so it will not be updated. But you can see in memory, the memory 78, there will be somewhere over here, there will be a change. Oh, simple. Let's look at it again. Something's happening. Oh man. Anyway, that's all for today. So we cannot my admin studio just restart. Okay, I will send you guys this code and then please play around with that. Okay. So let me send you the project. Was it this one? Yes, this one. So where can I send you the code?
When you will upload this record?
Straight away, right away after this. I just copy in Word and then or maybe in a notepad. Then you can just.
I mean the record, the video record for this.